Hi, I'm Mrs McTaggart and this is lesson number 7, the final lesson on vectors for higher maths. So in this one we're going to be looking at other properties or uses of the scalar product. So we're going to be playing around with it and doing some different wee things. Now, one thing to remember here is that normal laws of maths can also apply to scalar products. So we know the scalar product is A dot B, and there's two different formulas for that from our formula sheet. But if we have A dot B, we can also write that as B dot A, and we can just reverse it. And then if you have A dot bracket, you can just expand brackets as normal and times everything by A to make two different scalar products here, A dot B and A dot C. And that's what we're going to be working with today. So a couple of examples. First one is to work out what A dot A is. Now, A dot A, to picture it over here, is just when you've got a vector on top of itself. So A dot A would be whatever the magnitude of A is, times the magnitude of A again, times cos of 0, because there's no angle there. And cos of 0 is just the number 1. So it's just going to be the magnitude of A times the magnitude of A, which is just the magnitude of A squared. And cos of 0 is just 1, and that's coming from your cosine graph. Remember, it's 0, your cos graph is up here at number 1. Okay, so next one is just A dot B plus A dot C. So this can be written as A dot A plus A dot C. Now we already know that A dot A is the magnitude of A all squared, and then A dot C would be magnitude A, magnitude C times cos of whatever theta was. Similarly, we can do the same for below. We can write that as A dot A plus A dot B plus A dot C. And then we can go and think of, well, A dot A is just magnitude of A squared. And then A dot B would be magnitude A, magnitude B, cos, and I'm going to call it theta 1. And then the next one would be magnitude A, magnitude C, and cos of theta 2. Next, let's bring it into actual context and put some questions in. So I've got a picture here. We've got two vectors, A and B. We're told the magnitude of A, the magnitude of B, and we're told the angle between is 45. Both my arrows are pointing out, so that's not bad. I can work with that. So A dot B would be A dot A plus A dot B for my expansion. Now A dot A is just A squared, and we're told that the magnitude of A is 2, so that would just be 2 squared, which is 4, just working down the way. A dot B can be written as magnitude A, magnitude B, and then cos of the angle in between. So that would be 2 times 1 from the question times cos 45. So that would be 4 plus 2 times, now cos 45 is 1 over root 2. So that would just be 4 plus 2 over root 2. If you wanted to combine that, moving over here, that would just be the same as 4 root 2 over 2. Sorry, 4 root 2 over root 2 plus 2 over root 2. And you could combine it into one fraction and say 4 root 2 plus 2 all over root 2. Like that. So that would be that one. If you didn't follow what I just did there, remember you can also do a wee bit of smile and kiss. So at this point, you could have treated this as 4 over 1 and done smile and kiss and got 4 root 2 plus 2 all over root 2 as well. Okay, sometimes I do different ways of doing fractions and it depends what you've been shown. Similarly, here's another one. We're told what A, B and C are, but in terms of I, J and K. So first thing I'm going to rewrite these. A is going to be 2, 4, 1. B is going to be 4, 3, 5. And C is going to be 3, 2, minus 1. Okay, so our expansion for this will give us A dot B plus A dot C. And A dot B would be just multiplying everything and adding, so that would be 2 times 4 for the x's, plus 4 times 3 for the y's, forgot to put brackets in there, plus 1 times 5. And then I would add on A dot C, which would be 2 times 3, plus 4 times 2, plus, I'll just squeeze it in, 1 times minus 1. So, tidy all this up, we have got 8 plus 12 plus 6, plus another 6, plus another 8, and then take away 1. So I have got 20 plus 12 is 32, 40 take away 1 is 39, so the value there would be 39. That's that example done. My final example is the biggie. This one we're looking at an equilateral triangle. All the sides are 2 units, so the magnitude of all my sides is worth 2. Okay, so A, B and C are all going to have the same length. They're all going to be a magnitude of 2. An equilateral triangle means that all my angles inside are 60. But one thing I need to watch is my arrows are all going in a clockwise fashion. So let's do our expansion first. So we've got A dot B plus A dot C. Right, so we're going to be magnitude A, magnitude B, because there's no actual vectors given. We're talking magnitude ones times cos of theta. Then we're going to be magnitude of A, magnitude of C, and then that cos theta. So I'm just going to call that cos theta 2, and that would be cos theta 1. Right, so if we're looking at the vectors A and B, let me get out a different colour pen. A and B are these two vectors here. Now notice the arrows are going different ways. So I'm going to have to extend a line. So I'm going to extend this one here. So I'm going to make this vector A. And now both my arrows are pointing out the way, so I'm actually going to be using 120 for my angle in here. So they're all magnitude of 2, so I'm going to have 2 times cos 120. For the AC one, again, it's going to be 2 times cos. Now, for A and C, again, they're both kind of pointing the wrong way. So I am going to extend my C vector. I've got the wrong pen again. So I'm going to extend my C vector. So this is now vector C, and this would be 120 on the outside again. So both my angles are cos 120. Now cos 120, if I go to my all sine tan cos table, cos 120 would be here. The associated angle we use to the horizontal is 60. So these would both be the same as 4 cos 60 plus 4 cos 60. Cos 60 is a half, so I've got 4 times a half plus 4 times a half, which is just 2 plus 2, which is 4. So the answer here would be 4. So that's just some other ways that you might be expected to use a scalar product. Have a look at some past paper ones like these, and good luck. Thanks for watching.